how the sun generates energy. The sun's energy generated by nuclear fusion between hydrogen to helium. And you can see that the chemical composition of the sun, how much percentage of hydrogen is there, above 90% helium, and a bit of very less than 1%, only 0.1% of other elements are there. Yeah. So coming to the layers of the sun. So inside there's the structure of the sun. Inside there's a core. As you can see, the core is there. Then a radiative zone is there and a convective zone is there. Beyond that, then the atmosphere comes, which is divided into three layers: the photosphere, chromosphere, and corona. The inner sphere, as you can see, and as the name also suggests, and the terms also suggest, in the core, the helium the nuclear fusion reaction is happening. From a lot of heat is generated in a nuclear fusion reaction. The heat comes out, is radiated out through the radiative zone, which is followed by the energy being transferred to the entire body through the convective zone. And then the energy keeps emitting out, right, into the atmosphere, which is the photosphere, chromosphere, and corona. So, as it says, there's no real surface in the sun. It is gaseous all the way to the center. And energy is created in the core when hydrogen is fused to helium by nuclear fusion, and the energy flows out from the core by radiation through the radiative layers, and then by convection through the convective layer, and by radiation to the atmosphere of the sun. Now, as you can see in this picture also, from core, the energy moves out to the radiative, to the convective zone, and then the convective zone through convection helps the energy move out into the atmosphere of the sun. The hottest portion of the sun is the core, where this nuclear fusion reaction is happening. And when we talk about the atmosphere, the photosphere, chromosphere, and corona. So photosphere, which is the lowest layer of the sun's atmosphere and the coolest layer, followed by chromosphere, which is a slightly reddish region of the sun, followed by corona, which is only visible during total solar eclipse, as we see like a diamond ring. And otherwise, the white, those kind of gases that we see during total solar eclipse, that is corona. Okay, so it appears as white streamers or plumes of ionized gas that flow outward into space. Now, when we talk about the temperature of the sun's atmosphere, as you can see in both the graphs, which are same, the temperature by the time it reaches out to the corona, it is extremely high. So if we say the highest, portion of the sun's atmosphere which has the highest temperature, that is corona. Okay. Now, talking about photosphere, it has a temperature of 5800 Kelvin. And on the photosphere, several activities of the sun are seen, which you must have heard also of sunspots, solar spheres, flares, and solar prominences. Now, sunspots, what are they? They are the coolest portions in the sun's atmosphere. Now, sun already is very hot, but it is cooler. Imagine when the photosphere temperature is 5700 Kelvin, for sunspots, it is 3700 Kelvin. And they appear as dark spots on the surface of the sun. Now, the interesting part is, why do the sunspots occur in the sun? So it happens because of differential rotation. Normally, as we live on Earth, and we know that the entire body of the Earth, the entire sphere of the Earth rotates in 24 hours. That is one day, right? So the entire body of the Earth is rotating in that one speed. But what happens in the sun? As you can see, at the equator, it takes 25 days. But at the North Pole or at the poles, it takes 35 days. So there is differential rotation of this entire structure of the entire body of the sun. Because of this differential rotation, most of the activities occur, which we'll be talking about, the sunspots in the sun. Because of this differential rotation, what happens is these just like a typical, like in Earth, we see there's a typical magnetic field that will be there, which extends from the North Pole of the Earth to the South Pole of the Earth, right? So similarly, in other celestial bodies also, the same thing happens. But this is also maintained by the rotation of that particular celestial body. Now with Sun, since it has differential rotation, all the parts are rotating at different, much different speeds. Because of that, this magnetic field also gets all haphazard and haywire. Everything goes everywhere. So because of that, these kind of very specific localized magnetic lines, magnetic fields are generated, which have their own poles of magnetic north and magnetic south. So there are several magnetic north and south poles that are generated within the sun structure because of differential rotation. And they will always occur in pairs. Now, what happens is, because these, as they say that these magnetic field lines, these are so strong, they're 1,000 times stronger than the overall magnetic field of the sun. And because of this very strong magnetic field, the heat that is supposed to come out from the photosphere and the core, the heat is coming out, that gets trapped within this extremely strong magnetic field. Because the hot air gets trapped, that's why this area of sunspots are actually the coolest regions of the sun. And that's why it is almost 2000 Kelvin lower than the normal temperature of photosphere, which is 5700 Kelvin. You can see this, what I explained right now, you can see this in all these diagrams. Look at the first diagram first. As the rotation is happening differentially, you can see that how a magnetic field, a random, sunspot kind of a magnetic field is generated. Even in the next pic, you can see, and in this animated diagram, you can see how the sunspots are being generated, right? Again, here also in this slide also, you can see how the sunspots are generated. Because of the magnetic field generation, these small magnetic field lines that are being generated. Now, now what happens is, normally our sun has a cycle that it goes through, which we call the solar cycle. Its time period is 11 years, 11 to 12 years. That's how our Kumbh Mela has also been designed, which occurs once every 12 years. The proper Kumbh Mela occurs once every 12 years, and we are going to have that the next year. Now you will see how it aligns with our solar cycle of 11 years. What they say is that the entire structure of the sun's global magnetic field changes on a 11-year cycle, where after 6 years we'll have a solar minima and then a solar maxima. As the term suggests of solar minima and solar maxima, it means that during solar minima, there will be lesser solar activity. Hence lesser sunspots, lesser solar flares, solar winds, right? But when it comes to solar maxima, there will be much larger sunspots, prominences, and flares. For example, and also that when the next cycle starts after 11 years, the magnetic field poles are reversed. Now, one of the previous solar minima was in 2006. And as of now, we are going through a solar maxima, where the peak sunspot activity is expected in 2025, which is next year. So basically, we are going through a solar maxima. As you must have also heard in news, a lot of disturbances, a lot of telecommunication disturbances have happened in the recent past, especially the last 6 months. Since November, December, I'm hearing this news actually since last year, that a lot of aurora, and because of these only solar flares only, we get to see aurora borealis, the northern lights that happen. And this time you must have heard that aurora borealis, northern lights are being seen at much lower latitude as compared to something that was visible only in the Arctic region, the Arctic latitudes. But it is being seen now at much lower latitudes, both in Europe and US. Like even, so I know somebody who lives in New Jersey is able to see aurora borealis, which was not a common phenomena. It is happening because of solar maxima. And recently also, there are constantly news coming in that there is anticipation or apprehension of some kind of a solar flare, and hence disturbance of telecommunications going to happen. So talking about, like now we have talked about sunspots, talking about solar prominences. These are kind of protrusions from the sun's surface. As you can see, a large bright feature extending outward from the sun's surface. Now, when these kind of emissions that happen on the sun's surface. If it's a violent explosion, that is called a solar flare. And a large amount of energy is released in solar flares, and they may last for 10 minutes and will produce more energy than a million hydrogen bombs. Now, when these solar flares, which are like violent explosions on the sun, when they generate a lot of plasma and ions on the in the atmosphere. Now, when they are released into the solar system, into the space in the solar system, that is when it is called a solar wind. The solar wind is a stream of energized charged particles, primarily electrons and protons, flowing outward from the sun. And they cause magnetic storms. They interact with the magnetic poles of our different planets, and they cause auroras, northern borealis. And not only on Earth, even we get to see auroras on Jupiter and Saturn, as you can see in the pics. And even for comets, this is the solar wind that blows the tails of comets back away from the bodies of comets as they go through the solar system. Now, as I was explaining, that the sun, which releases these solar flares, these ionized particles move into the Earth's atmosphere, interact with the magnetic field, and they result in the polar lights, and also causes different kind of interferences like radio, power grid disruptions, satellite microchips damages, etc. Now that we talk about the sun, it is important to mention a bit about the Aditya L1 mission, which was our mission of ISRO of India. And I am sure that you are all following up with what is happening with Aditya L1 mission. But just to give you a brief and a background and kind of a revision to what has happened in the past year, is that Aditya L1 mission, as we all know, the launch was very exciting. It happened just 1 month after Chandrayaan was also launched. So through various maneuvers, it left the Earth's sphere of influence exit, and it was meant to enter the L1 Lagrange 1 point, where it is on a halo orbit. Halo orbit, we all understand, I hope, that halo means it is not a real orbit. Like, for example, Earth revolving around the sun is an orbit, is an orbit, right? It is not halo. But around the L1 point, it is halo because it is exactly not revolving around it is revolving around a very, around a point. It is not revolving around a celestial body. But so that is what an L1 is. L1, there are 5 Lagrange points. Any two celestial bodies will have Lagrange points, and there are 5 points usually. As you can see in this diagram, very beautifully explained what would a L1, L2, L3, L4, L5 points mean. L1, as you can see, will be between the two celestial bodies, where there is complete balance between the if you draw a perpendicular line between the two, there will be a stable point, and that is what the L1 is. L2 will be behind. As you can see, L2 will be behind a particular celestial body. L3 is behind the other celestial body. L4 and L5 are again far. So L1 is the most convenient point where we could have launched the solar mission, because it gives us an uninterrupted view of the sun at all times, irrespective of what is happening on Earth, what satellites are there. L1 gives us an uninterrupted view of the sun, and anything that is being released from the sun, we get the direct influence. Means Aditya L1, our spacecraft would receive all direct information, any solar flares, any solar winds that would be coming towards Earth. That would be the first place where they can receive the information, right? And as they can say, that this location allows the satellite to access solar radiation and magnetic storms before they're influenced by Earth's magnetic field and atmosphere. And it also gives you gravitational stability. So there it can stay for a long time. Even the other solar missions that have been launched by other countries are also at the L1 point. And yeah, the mission is kind of to stay, at least as of now, the lifeline of the mission is for 5 years. And it is good to know that the L1 mission was launched around the solar maxima time. So we can really get a lot of information. And over the 5 years, by the time it reaches solar minima, we can gather a good amount of information as to how and what changes are happening with the sun, and how it may influence the Earth also. Now, so going back to the timeline of Aditya L1, how the launch happened on 2nd September, followed by finally on January 6th, Aditya L1 reached the L1 point. Now, to take the readings of to take readings, different readings of what kind of emissions are happening from the sun, there are different kind of payloads that are present in Aditya L1. Going into the details, the different payloads, as you can see, VELC is a coronagraph, which will help read the corona. SOOT is an ultraviolet imaging telescope, helping in reading the sun through the ultraviolet range. There's the Solex, Helios, as you can see, these are X-ray spectrometers. Then Aspects and Papa, they will help you read the solar wind and plasma analyzers, and magnetometer, helping in reading magnetic lines. So the major science objectives, the different kind of studies, and spectral lines will be, spectral analysis will be done, lot of studies will be taken, UV imaging will be done, so that we get information about what is happening with the sun during this period. Some of the solar missions that have happened worldwide, ESA is European Space Agency, JAXA. Okay, so these are some of the solar missions from around the world and in different timelines. Now we all know about the solar eclipse, right? Yeah. Now, as we were discussing for the corona, that the corona is visible only during a solar eclipse. Okay, total solar eclipse. Now to go to read a little bit about how corona is being read. Different kind of spectral lines are read for corona. There's the K, F, E, and T corona, as you can read. That K corona reads the scattering on electrons, F corona scattering on dust particles, E corona emission lines produced by ions in the corona, and T corona thermal emission of dust particles. Now, as you can see in this graph also, like this is the relative intensity. So the intensity of the of corona is like equivalent to a full moon. It is so less, it is equivalent to a full moon. Now, normally you will not be able to see, but during sky, during totality, you are able to read the see the intensity of corona, which is equivalent to a full moon, which is so less, and that's why the sun's main light needs to be shielded in some way, so that you are actually able to read what's happening with the corona. Now you read these different spectral lines, they are being recorded, and during eclipses especially, these lines are recorded. That helps understand with the structure of the sun. Now, this is something that you should also read. What it says is that the solar corona is diffuse hot plasma extending a solar radius or more above the surface of the sun. And the corona is only visible in white light during total eclipses, because its intensity is about only 10 to the power minus 6 of that of the sun's days. Now, this information is important because the next slide I'll tell you about what happened during Aditya L1 mission, and why the recent solar eclipse that happened in April, and how it has an impact on Aditya L1 mission, and how both are correlated. So just getting this information helps in understanding the next slide. So the observed light has several components, the different kind of the studies that are being taken by studying the coronal structure, which is through F corona, K corona, and E corona. These lines and these kind of studies are taken. You can just simply read it. And now this is one of the examples, one of the images that has been captured by a coronagraph, which is also there with us, VELC. Now, what has happened during the recent solar eclipses, that normally as the intensity is so low, we cannot study the corona normally from the Earth. Plus, there are so many other disturbances in the sky and the atmosphere. So one has to put up this solar disk to read the corona. Now what has happened is, this coronagraph, which is already there in Aditya L1 mission, which is located at the L1 point and is having an uninterrupted view of the sun and all the energy that it is getting from the sun uninterrupted. It has a solar disk, so that the main light of the sun is blocked, and it is able to read the corona like this. Parallelly, when total solar eclipse happened on the Earth, scientists went to the concerned location. They took the recordings because they could directly see what was happening with the corona. Now, these two studies will be correlated and estimates will be made as to how accurate our studies are, what kind of inferences they can come up for the same. So that is how critical and how interesting this study became, by a total solar eclipse and having a solar mission out there at L1 point. These are some of the images which shows the different lines, like an FE 145303A green line image of the corona of March 2002 from the National Solar Observatory. How these images are taken and further studies are done. Another line that has been, another image that has been taken. And they say that the E-corona is best observed in the extreme ultraviolet and in X-ray, but because the atmosphere blocks these short wavelengths, the observations must be made from space. And here again, it says the same thing, that the spacecraft offers scientists the opportunity to see and study the corona of the sun as seen from space and as viewed from the ground during a total solar eclipse. The VELC, or coronagraph, that is present in the Aditya L1 mission, creates an artificial solar eclipse to study the sun effectively. Due to the eclipse, nothing special happens to the sun. It's only the VELC spectroscopic lines which will be operated in raster scan and sit and stare mode of operation to observe the coronal structures in emission lines. So this is how a joint campaign has been made to corroborate with ground-based observations. So as I said, a reading taken at L1, at L1 point, a reading taken at solar eclipse in April 2024 on the ground on Earth. Both the studies will be correlated, corroborated, an analysis will be done. And comprehending the corona's dynamics is essential to understanding how the sun's heat and energy are transferred into solar wind and how it ultimately affects our solar activity on the Earth and all the storms, that geomagnetic storms that we keep talking about, right? Because as we all know that these are very essential to our satellite operations and communication systems. Now, what experiments was carried out by the Indian team during the eclipse? The Indian scientists took a reading in the green emission line of this as I showed the picture before also, for another similar FE line. And yeah, so I have covered this also, that solar corona is only visible during total solar eclipse. So one needs to block the solar disk artificially using an instrument called coronagraph, and artificial coronagraphs suffer from scattered light and it becomes difficult to see the inner corona. But during a solar eclipse, the moon, which provides occultation perfectly and blocks the solar disk, makes the inner corona visible. So essentially, that is how comparative studies are being made. And one of the results that came out initially during very initial days of Aditya L1 data that was released by the suit, the UV capturing payload that is there, which captured full disk images of the sun in near ultraviolet wavelengths. And that was one of the, the benefits of Aditya L1, that it was the only solar mission that was capturing in near ultraviolet range, near ultraviolet wavelengths. So some of the image that was captured. And quickly just going through the life cycle of the sun, because sun is a star, so just quickly going through what and how stars function and what's going to be the future of the sun. And that is that we are at a very perfectly fine, perfect, mature, young, we are enjoying the young life, the youth of sun. And many billion years later, it will turn into a red giant and then a white dwarf. And it's people usually ask why sun would not result in a black hole, is because it's only of a star 25 times the mass of the sun that it forms a black hole. But sun will not form a black hole. It will, when it is to die several billion years later, that is when it will form the red giant and then a white dwarf. And it's only when life cycle of a star with 25 times the mass of the sun, that is when it will form a supernova and a black hole. And it can also lead to a neutron star, or which will lead to a pulsar, which is a very quickly rotating object in space. And they tend to emit light from its poles And when they reach to the earth, it looks like it is pulsating, because that is how we receive the information, and that is how the name pulses came into being, because we receive pulses of light, but it is rotating at a super high speed, and that's how and it's emitting all its energy that is there. The burnt out star, it emits all that expended energy into space, and that is what we receive as pulsating, so pulses. So that is it. And yeah, so we have covered the overall uh, features of the sun, how the sun functions, how the sun is, how the energy is being, how it affects us, why the study of the sun is important, and the solar mission and how it affects us, and what kind of good studies and what kind of analysis, and how it can help us directly to understand and help the how it can impact our how the solar activities impacts our daily communications, and all this information helps us uh, understand from a very scientific viewpoint also, uh, and satisfies the curious nature of scientists, the most important, the only star of our solar system, and how it helps keeps our solar system together. So thank you. That is what I wanted to share with you all today. Somebody asked, what is the effective way to understand? Is it because of the convection? No, convection has no relation to differential rotation actually. Convection, it is a phenomena that has been observed in the sun. Like these, if you, it is about, when people are studying about sunspots and all the research papers that you read about sunspots, what I find is that they are constantly saying that it is a known fact that there is differential rotation happening. And so sunspots are generated. And then further studies are done to understand. The studies are mostly, what I read is to understand when the next sunspot may happen, by taking into consideration all the past information that is there, and kind of doing a modeling study, and then anticipating the future maxima or minima in terms of like sunspot generation, because it helps us, because it affects us directly when there is too much of solar activity happening. So it's just to out of scientific curiosity also to have these kind of studies. So that's what I would like to say on that. Others can just comment something. Can we say the magnitude of, wait, can we say the magnitude of the solar spheres depends on the distance between the sunspots? On what basis do you say that, is the question. Can we say the magnitude of the solar flares depends on the distance between the sunspots? Uh, are you saying within the sunspot? Because one sunspot and its magnetic field will be defined, right? However, the sunspot structure is. No, solar flares, see, like solar prominences are generated irrespective of irrespective of anything. Solar prominences are generated, and then there are violent explosions happening, because suddenly there is this. I think everything is related to the amount of nuclear fusion reaction is happening, and it somehow happens and has been observed that there is a solar maxima, solar minima. During solar maxima, more of this more of this nuclear fusion reaction is happening. More heat is generated, and sudden violent explosions happening, and that is what results in solar winds or solar flares. So you cannot correlate these two things, because these are solar prominences, sunspots, solar flares, these are all activities happening, but ultimately it all starts with that nuclear fusion reaction, increased solar activity, increased nuclear fusion reaction, because of which a lot of heat is generated, because of something is happening. Solar cycle is of 11 years, such that every 11 years its magnetic field flips the poles. Have I got it? Yes, yes. Yeah, that's what, like the magnetic field flips, the global magnetic field flips. We saw that last solar minima was in 2000. Doesn't that mean next should be, sorry, I couldn't get this. Next should be after 22 years. Actually, I was just reading, yes, that overall they do calculate in 2022, but I actually did not calculate this way. But it is said that right now, so it is like it's a stretch of thing. It's not like today it's happening and then from tomorrow it's a solar minima is starting. It's a gradation. It's a graduating thing, right? So you just so people are just I see 2006. I'm not very sure, but I am very sure of the fact that 2025 and 2024 this time a solar maxima is going on. So calculate accordingly. Okay, 2006 could also be a wrong information. So what is important is that at this point, solar maxima is happening, and you can see that around in the world. You can see that, and let's see what happens and what kind of results we get from Telvan and other solar missions also. What exactly is happening, and this is an observation that we all should kind of keep our eyes open to over the next 12 years and see how our lives get affected and what is happening around us. Uh, in terms of in the world what is happening, how is the solar activity getting affected or is affecting us as people on earth and our communications. So that is something that is an interesting study and we all can do it at our own homes. Harshvardhan, I cannot comment on that. Cannot comment on that at this point. The sun's corona and the surface temperature. What was the surface temperature? And sun's corona. Why there is huge temperature difference between sun's corona and its surface temperature? See, by the time the heat is getting released into the atmosphere, I think being gaseous, the temperature rises a lot, and probably because of these volcanic kind of, not volcanic eruptions, sorry, solar eruptions that is happening, it just adds up to that heat, probably that's why the temperature at the absolute outside is extremely high because the heat is constantly getting released outside. So that could be one of the reasons why it happens. Is that absolutely hotter than the surface itself? Yes, it's quite interesting how this relatively cooler spots are letting out flares. But there was never a comment on it's the sunspots which are leading to solar flares. Like we are not correlating that okay, sunspots are leading to solar flares. There are different phenomena that is happening on the solar atmosphere, which is solar prominence, so sunspots and solar flares. All are though of course there has to be some kind of a correlation, but yet they are also independent of each other. So saying this question itself kind of says as if it's the cooler spots which are responsible for letting out flares. No, I don't think there is a direct correlation that you can make, right? So it's a phenomena, one of the phenomena that is happening. Solar flares, another phenomena. Yes, what you can directly say is solar flares are responsible for solar winds because solar flares are happening, a very strong solar eruption is happening, and then from there, the energy is getting released into the space, which is the solar wind. Yeah, that is a direct correlation. But here, I don't think you can just directly correlate it that way. Oh, cool. Good questions. Thank you so much. You all heard it well, and I'm very happy about it. I hope you all could take something good from this session, and hopefully you are interested in the sun and can take the studies forward in the future. Pursue studying sun and generate more. What do you call? Be part of the next future solar missions and discover something really new about how the sun functions and how the sun is for all of us. Thank you so much for attending, everyone.
Thank you so much. If you have any other questions, we can. It's quite interesting how.
How L2 point is stable point in a solar, although it is outside the line joining Earth and mechanics, how we decided. No, I don't decide it, nor neither we decided. It is these Lagrange points are standard. As you study more, you'll realize, or just Google it also. So these Lagrange points का concept ही यही है कि बस 5 points होते हैं between two celestial bodies. And it has been found by scientists that these L1, L2, L3, L4, 5 points are there at those particular positions, as you will see in the diagram. And where they have found that between two celestial bodies वहाँ पे stability पाई जाती है. We could have launched it in L2 also, L3, L4, L5, हर जगह launch कर सकते थे, but you can also see the distance. So comparatively, L1 is the closest, the most easiest to reach, the best position that we could have reached, and direct access. Is such a what better than that, right? So that's why L1. It has been found that there is stability there. That's why.
Okay, we have
Lagrange, so you can observe the sun. No, we don't need to launch it at more Lagrange points. Exactly what I explained right now. Because we don't need to. Yeah. We don't need to launch them, right? Because L1 is the best point. और आप सोचो ना L2 तो moon के पीछे था, I guess. Where was
yes.
L2? So why do you want to go backwards and get blocked? You want to move for like want to see from the front, right? मेरे पीछे क्या है? Then I will block the view from the audience, right? To what you can see behind. So why will I put something in front of get a celestial body in between? Direct view चाहिए, direct view लेंगे. Simple.
So any other doubts and query related to the presentation? So, magnet Harshvardhan again,
Why are
ma'am.
the poles flipped in the two hemispheres of the sun? Why the two hemispheres of the sun? Two poles flipped? No, there was no two poles flipped in the two hemispheres of the sun, and I also didn't focus anything on the hemispheres of the sun. It was irrespective of any. I was not focusing in northern hemisphere में कुछ हो रहा है, southern hemisphere में कुछ हो रहा है. I just said that the sunsports are having their own magnetic field. They have their own north pole, south pole. The magnetic field is very strong. I didn't say anything about these things at all. I just said that during solar cycle जब चेंज होता है 11 साल बाद तब जब ग्लोबल मैग्नेटिक फील्ड एक्सचेंज होता है दैट्स ऑल आई सेड it is a study they have found all these are all studies that's what like these are all kind of the studies that have been done on sun and that's how we get all the information a lot of calculations happening you can find out and study and read the research papers so that's what my intention of this lecture was that it generates enough curiosity within you so that you go back now you find out the information now you understand the specifics of if there's something that has interested you really and sunspots yes is the most exciting part the differential rotation is the most one of the most exciting parts corona is one of the most exciting parts of the sun go back read research papers now don't read just simple text go back read research papers google them and try to understand more phenomena and more details of how these kind of studies must have been done that is something that now you have to go back the information that will be released by aditya L1 mission also now all of the information that will be released in general public will always be very simple but if you really want to understand the code the mathematics of it the details of it. For that, you have to go back, read the research papers, find the original text that has been written by the scientist, and then try to understand and correlate between what is happening. So that is a study for you to do. This is just a way to generate enough curiosity so that you can take your passion and curiosity and your studies forward. Okay. So this thing that is for, sorry for the lag. I meant in the northern hemisphere, all the field for the original certainly. No. This is just a picture. It is nothing. I didn't want to demarcate anything about northern and southern hemisphere. It was just बस वो एक image था. So don't go by that. Hmm. What processes is responsible for changing the suns? This is a result that has been found. It has been observed. And please understand that when it comes to sun, most of the information is not available. Because people are still trying to understand because it's not easy to study the sun for obvious reasons. We cannot reach like in the moon. We cannot just send a probe like in the moon. So to understand these are all a lot of very difficult to study. So many solar missions have been sent, and there is a lot of limitations of what kind of analysis for the sun can be done. So I would always recommend you please go back to all these boot camp sessions that you had. Whichever portions have interested you, whatever you have liked, just go back, read research papers now. Don't go into reading simple stuff and try to see if you can find answers to what is happening. Okay. And all the latest missions, especially for Indian missions, go back and read core research papers released by the scientists कि exactly क्या हो रहा है. अभी जैसे मैंने अभी total solar eclipse का बताया कि क्या what they plan to do. Now go back, see, find what information can you find. What kind of corroboration studies have been done? Has it yet been released or not? Just see, check them out. That is now for yours to do. Okay. I think I'm getting the same questions about sunspots. Uh, when the change
Electrons.
no. As I said, it is not about equator or North Pole or South Pole. It's just sunspots है बस सब जगह ही हैं sunspots. हाँ. Yeah. Good. Thank you, everyone.
Thank you, ma'am. Thank you once again
Prerna ma'am.
for coming online and sharing your experiences and knowledge regarding the sun and the missions related to the sun
Yeah.
and observations. So
Thank
I
you.
think this will definitely benefits the students in their further studies. So hope to see you again in
Thank you
some
so
of the
much.
sessions at the
Thank
planetarium.
you. Thank you.
Thank
Bye
you.
bye, everyone. Thank you so much for attending. All the best to all of you.
So, again, I just wanted to let everyone know that we do have a session at 1